Okay, so we've been discussing these tests for convergence of series. And so last class, we sort of went through the comparison, the limit comparison, the ratio, the root. And really, the best way for you to learn these is to do them, and you're going to struggle at first. This is it's a topic that, every year I've been, teaching calculus for 15 years or something at, at this level. And, no matter who we are, students struggle with this. It requires a lot of practice. So let's do some examples of some series. So the one I'm looking at right now from homework is, so basically we're going to ask this. Does it converge? And more importantly is why. See, again, there's two options here, converges or diverges. No one needs to know that you can flip a coin in your head and say it converges. What we do want you to be able to do is give a logical argument for why it either converges or diverges. And this is not an easy skill to learn. In fact, it's a complicated skill. There's lots of abstract things happening. There's lots of symbols, as you guys know. Just looking at the way the problem is written. So on the homework, for example, I just give you this. This is K or P on the homework. So I literally just spit out this creature. And so right now, if you just look at this as a human being, I don't care who the hell you are, part of my language, that looks scary, right? It's just scary looking. So when you're sitting there like, what am I doing? Well, you're normal. It's scary looking. It's overwhelming. So the first piece of advice I can give you when you're studying these series is to not get overwhelmed, but this is just good practice all around. Write out the first few terms. Even though I didn't do it on the homework to save space, and even though you don't really see it in the books, write them out just to get an idea of what you're working with. So what is this? Well, let's remind ourselves what this scary symbol means. It first means put in k equals 0. So when I plug in k equals 0, I get 1. Then it means add what happens when you plug in k equals 1. So when I plug k equals 1 in, I get 1 over 2. Then I'm plugging k equals 2 in. So this is, I can't really do anything, but I could write this as 2 to the 3 halves plus 1. And then the next term would be 3 raised to the 3 halves plus 1. And so that pattern continues. Now, of course, you could go to a calculator and find out what each one of these are, but that's not important. What's important here is we're just writing out the first few terms to see what it is. I mean, what is, I guess you could do this if you wanted. You could say, okay, what is 2 to the 3 halves? Well, maybe some of you, when I was a kid in school, we practiced those kinds of things. You guys might not have. 2 to the 3 halves is the same thing as the square root of 8. And so really, if you wanted, you could write this as 2 root 2 plus 1. If you're familiar with that. And what is 3 cubed? Well, 3 to the 3 halves is the square root of 27. I don't know, can you do anything with 3 to the 3 halves? Maybe some of you are good with your exponents. Maybe some of you aren't. Again, what does it mean for this particular problem? It doesn't really mean anything that you can tell me what this is, because this has nothing to do with whether it converges or diverges. But you might remember that 3 cubed is 27, and 27 is 3 times 9. So you could write this as 3 root 3 plus 1. And then, of course, this goes on forever. So let me be absolutely clear here. This stuff that I've written on the right-hand side, me writing out the first few terms, I'm not technically asking you to do that. And really, that doesn't give you any insight on how to answer the question. But what it does do is it gives you practice working with these series. So first off, does everybody understand that? I'm just trying to give you guys a way to get a feel for what you're doing. Okay, so here's now my thought process. My thought process is, does this thing converge or does it diverge? Now, I have experience. That's something that you guys lack. So how do I use my experience, and how do you gain experience? Well, the first thing screaming at me is that it looks to me that I have something that resembles a P-series. It isn't a P-series, but it resembles one. So if I go to the next page, let me write that down, because this is important for me to note. So this is just for me. So note, this part right here looks like a P-series. Okay, so again, it looks like a P-series. I didn't say it was, but it looks like it. That K raised to a power suggests to me that I might want to try comparison with a P-series. All right. Again, why does it tell me that? Because I have experience. It might not say that to you. You might just look at that and see hieroglyphics. You just might see a jumble of symbols, and that's cool. You know, there was many years ago when I sat in and I opened the book and I looked at that and I had no idea what the hell I was looking at. It was hieroglyphics. And I didn't have pretty books like you guys have now with colors. I didn't have YouTube to look at. I didn't have Google. So it was a little more overwhelming for me. Okay, so here's what I'm going to do. That suggestion or that hint, or it looks like a P-series, makes me think to try that. So that's what I'm going to try to do. So the next thing I'll do is note that this suggests comparison with this guy. Might work. Notice I didn't say it will work. I said it might work. So this is my scratch work I'm doing. You know, I've mentioned this to you guys many times. You don't just write homework and then do problem 1 space, problem 2 space, problem 3 space, and then expect everything to fit in. When you're doing calculus homework, a lot of it is scratch work. A lot of it is trial and error. You can't do this now, but my advice is always go to the library and get all that junk paper that nobody uses, all the scratch paper. Take it home. That's where you do all your learning. Very often, to get the answer, you have to try and fail at a few attempts. In this case, this will work right away. And what I'm going to do is switch colors, switch to green. So here's what we want to notice. So notice that if K is greater than or equal to 1, that this guy, 1 over K to the 3/2 plus 1 is less than or equal to 1 over K to the 3/2. Now, if you can't see that, that's fine. But this is just basic number skills. And I'm not saying seeing it's basic, but that inequality I have written there is basically saying if I have 2 fractions and one of them has a smaller denominator than the other, then it's very easy to see which is the bigger number. What's bigger, 1/10 or 1/100th?
10th.
Yeah, so what we do is we know this is true. Why is this true? Well, this is true since if you take reciprocals, this is bigger than this. I mean, look, that is the inequality at the bottom of the page is just fundamental. If I take a number and add 1, it's always bigger than what I started with, if the number is positive. If you take a positive number and add 1, your result is always bigger than what you started with. Which means if you take that inequality, if you take that and reciprocate it and write it as fractions, you get the opposite inequality. Okay, so that is the key observation in this problem. And now we can finish it. So how do you finish this problem? It's quite elementary now if you understand the previous stuff, which maybe isn't elementary. So since this guy converges, why does this converge? It's a P series with P equals 3/2. So since that converges, the comparison test guarantees this creature converges. So is this easy? No. Does it take time to learn this? Yes. And that's what you need to keep reminding yourself. And of course, as I say that, some of you are saying out the other side of your mouth with your microphone on, where the hell am I supposed to find all this time? Yeah.
Quarantine time.
Yeah, but the thing is I'm learning. I got kids stomping upstairs, outside. You know, one of the things you don't ever think about is what kind of resources do people have? What kind of access do we have to quiet time? Some of us might be stuck in a house with screaming people. Some of us might be in a small room or a big, who knows what everybody's situation is. Someone has a comment.
Another question.
Yes.
If the limit equals 0, can the series still diverge?
Oh, yeah. You mean if the limit of the terms equals 0? Absolutely. Yeah, that's the harmonic series.
Okay.
So here, let's write this down. So, and I want you to be clear. I'm going to write this down. We've done it a few times, but Kathy, I got to make sure you guys understand this, because usually you guys are you say things, but you're not saying what you mean to say. So here's what I mean by that. So here's let's write this down, and I want to try to remember it exactly as you said it. So here was the question. If limit is 0, can series diverge? So let's say still diverge. I think you used that word.
Yeah.
And the answer is yes. But let's be very careful. When you say limit, what limit are you referring to? If you're referring to the limit of the terms, then that's the divergence test. So the answer is yes. And the answer, or the prime example, is the harmonic series. So what is the harmonic series? Well, let's go to the next page to remind you. So the harmonic series is, if you write it in the shorthand, it's 1 over k. K goes from 1 to infinity. And what are these terms? This is 1 plus a half, plus a third, plus a fourth. So this guy diverges. How can you show it diverges? One way we used the integral test. However, the limit, now it depends on what limit you're talking about, Kathy. I would assume you're talking about this. However, if you take the limit of the terms, as they go to infinity, the terms are getting smaller, and in fact, they're going to 0.
Yeah, that one.
So yes, these terms are going to 0, but the series itself, even though they're all getting small to 0, if you try to add them up, it diverges. So I wish there was, I always say this is my stupid grading story, but if I had a pill where this just made sense overnight, I would give it to you. It just doesn't make sense overnight. And here's another thing you got to really keep in perspective when you're trying to learn this. Is human beings have been thinking about these issues since as far back as we have written history. They really have. And do not get it twisted. The reason you're having a hard time learning it is the same reason smart people throughout history have had a hard time. I mean, it took human beings thousands of years to figure this out. We didn't really start making sense of these series as humans until a couple hundred years ago. So humans have been thinking about these ideas for a long, long time. And it wasn't until a few hundred years ago where we started to actually make sense of this. So when you're struggling with series or anything in calculus, just remember, human beings struggled with this as a civilization for a long, long, long time. So we're asking you, you know, I mentioned this back in Calculus 1. When you take a calculus sequence, we're essentially asking you guys to learn in a couple semesters what took human beings, you know, a couple thousand years to figure out. Now, of course, it's easier to learn when someone else has made sense of it, but nonetheless, that doesn't mean it's easy to learn. It's just easier. So, you know, you got to keep that in mind when you're struggling with these things. I don't know if that makes you feel better, but that's what I would tell you to do, you know.
Okay, so if the limit of the term equals infinity, can the series that
No. If the limit's not zero, that's what the divergence test says.
Okay, because I was like, if it applies this way and the limit equals 0, then I don't know if it.
Well, do you have a particular example you're talking about?
No, it's just in my head. Because I was like, when we define convergence and divergence, we said convergence is like when the limit has a value or 0 or something, and then divergence was.
Well, it depends on what you're referring to. Convergence means convergence of what? Convergence of a sequence or convergence of a series? There's two different things. If you go back to the previous homework, I was trying to illustrate that a sequence and a series are two different things. So when you throw around words like, or phrases, I should say, like convergence of this or that, you have to be more specific to what you're talking about. When we say a series convergence, we're saying that the sequence of partial sums converges. So that it's a very delicate issue. Now, what the divergence test says, and that is a test for for series, is it says is if the limit is non-zero, then it has no chance of converging. So let me repeat this again very clearly. The divergence test says, and maybe I'll write this down to help, well, maybe confuse and or help. The divergence test says if you take the limit of the terms, so take the terms, and if it says if this thing is not 0, then automatically the series diverges. But it doesn't say the opposite. So like I mentioned this to you guys a few classes back. You know, one of the things that makes it hard to understand these statements is that many of us do not have much experience with this idea of how sentences and logic are stated. I mean, read this sentence. It says, if something is, you know, if some fact holds, then this must occur. So you have to read the statement, and it doesn't say the opposite. It says one direct way. It says, take the limit of something. And if this limit is non-zero, whether it's infinity or 7, and so if it's 7, then we know the series diverges. So an example where something like this would apply would be if you look at the homework, and you know, we can give you something like, well, let's look at one. So suppose I take this series. Let's take k goes from 1 to infinity of k plus 3 over 3k plus 5. Now look at these terms. The first one is going to be 4 over 8. And then you're going to add 5. Yeah, when k is 1, 4, when k is 2, 2. 5 over 11. The next one is 6 over, when I plug 3, 6 over 14. So these terms might on the surface look like they're getting small, but this guy diverges. Why does it diverge? It diverges because if I take the limit of the terms, what is the limit of the kth term? Take this sequence, this term, and ask her, what happens to this thing as k goes to infinity? As k goes to infinity, this equals 1/3, which is clearly not equal to 0. So what's happening here is if you go far out in this series, if I keep adding terms, essentially what I'm going to do for eternity is add 1/3 plus 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 1/3, and then I die. And then whoever wants to take over for me continues to add 1/3 plus 1/3 plus 1/3 plus 1/3. There's no way that that can ever be a finite number. So again, there's lots of mind, I like to call them mind F's, and these things really play with your mind. It's, a lot of times these things almost seem paradoxical. Like, it's once the moment you think it makes sense to you, and then you go get a glass of water, or you go play a game, or you go, talk to your friends, and then you come back 20 minutes later and you completely lost again. You're like, oh my God. So this is just one of those things. It doesn't mean you're stupid. It doesn't mean you're not smart. It means you're human.
So, which test do you go by over another one? Because in example,
say that again.
Because in example 2, if we use a divergence test, the limit would have equaled to 0.
Right. So then,
but the integral test.
When you say 2, do you mean what example? The one we're doing?
The second one, the one we did just before this one.
So you're saying if I take this thing right here?
The 1 over k, yeah. So the limit equals
doesn't apply. It doesn't work here because it doesn't help you. It doesn't say anything if the limit's 0. It says nothing.
Oh, okay.
It only says it only gives you something if it's not 0.
Not 0. Okay.
Again, this is that subtlety of the logic, and it's funny because some of you will go on to take classes where you do some more logic and study that stuff, and you'll think that it's annoying, but then once you study that crap, you'll look at this and you'll be like, oh my God, I can't believe I thought that stuff was so difficult. It's just one of those things. But yeah, so to rephrase, Katie, is the divergence test gives you nothing. It's worthless if the limit's 0. It's only useful if the limit is non-zero. So if the limit is 0, you have to try another test.
Okay. And
that goes with some of these things. Like I said, you could try the ratio test, for example, and if it gives you 1, if the ratio test gives you a limit of 1, it's useless. It did nothing for you. It was a waste of, well, not a waste of time, but it didn't give you any information. You have to try something else. It's kind of like if you open, if I want to go work on my car and I pull out a certain wrench and then I open the hood of my car and I want to move something and that wrench doesn't fit, well, then I'm screwed. I got to go get another wrench. Does that make sense? You have to get the appropriate tool, and not every convergence test, quote unquote, tool is always applicable. Now, on the other hand, sometimes you could use multiple tests. They would work on a series. Now, they're never going to contradict each other, but sometimes one is easier to use than another. For example, you could have, if you go to that very first example we did, problem P on the homework, you could have tortured yourself and tried to use the integral test. You may have gotten somewhere after 47 years, but it's much easier to use the comparison test. Similarly, look at J on the homework. If you look at J, first off, you could argue there's a typo because you could say I can't plug in 0 because it would be undefined. But assuming that I corrected that typo, what I mean by that is if you look at J on the homework, that should have started k equals 1, not k equals 0. It doesn't matter in general, but for this problem it does. But the quick answer for J is converges by the P series. You don't even have to comparison. You could say converges because it's a P series, P is greater than 1. That's all you have to say. But you could, if you wanted to torture yourself, go and integrate. But it's unnecessary. Does that make sense? Maybe. Sometimes I have nightmares of how hard this was to learn when I was a little peasant like you guys. Sometimes you just have to take a breath and then go walk and run into a wall or something. All right. Does anybody else have any questions on these homework problems while we're at it?
Yeah, I have a question on part S.
Part S? Sure, yeah. Do you want me to do it, or do you have a specific question?
Yeah, I just don't know which what to use for.
Yeah, it's a good question. So there's there's two sirens in S. So let's look at it. I'm not going to do the same one, but I'll do one similar. So this is our third example, right? So let's look one. Once again, I'm going to write it. So the first thing that screams at me is this -1 to a power. Okay? So I'm going to write it a little different than what you guys have. It's similar, but not the same. And let's say that n starts at 0 and then it goes forever and ever. So this is some shorthand for the following series. When n is 0, we get 1. Excuse me, I lied. We don't get 1. We get -1. Oh, no. When n is 0, we get 1. Who am I kidding? Yeah. And then when n is 1, you get minus. So this would be 3 over 5 factorial. Even though it's 120, I'll just write it like this. And then it's plus 9 over 10 factorial. And then it's minus 3 cubed is 27 over 15 factorial. And then this little creature continues. So does this guy converge or diverge? Well, here's what I'm going to do. So there's two things. So let's write it in a different color. Boom, 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 boom. So let's do this. So here's what I'm telling you to say. The factorial, which is this thing, screams ratio test. Now you might say, well, that -1 makes me think alternating series. And you could use that, you could, but my advice to you is let the factorial override that. The factorial, look, think of all the tests we have. If you're thinking deductive reasoning, if you're thinking what makes sense, the only test that even seems remotely plausible when you have factorials would be the ratio test. Now you might say, well, what do you mean, O'Grady? Well, let's think about it. Are you trying to integrate a factorial? Have you ever integrated x factorial? No, you haven't. Are you taking roots of factorials? Well, we've never really seen that before. Are you going to compare? Well, what are you going to compare it with? there's nothing there that looks like a p-series. There's nothing there that looks geometric. And so what you'll find the more experience you have is the more often you see factorials in a series, the more likely that you are to guess correctly to try the ratio test first. Does that make sense? Hopefully it does. Now let's show you how we can go about doing that. Let's get a different color here. I wish there was more colors on here. I don't know. We'll use this like weird red here. Okay, so the ratio test says we have to do the following. So what is R? Well, it's the limit as k goes to infinity. And we take the kth plus 1 term over the kth term. Now, as I said to you a week ago, when you're doing the ratio test, you are going to learn right away that everything looks ugly when it doesn't have to. So let's remind ourselves of what's the kth term here. The kth term is -1 to the n, but we're going to take absolute, or the k. We're going to take absolute value, so that doesn't matter. That -1 is pretty much redundant to us. So what does this become? This becomes the limit as k goes to infinity of, so this is 3 to the power k plus 1. This is the k plus 1 term. Over 5 times the quantity k plus 1. And then this is times, now I'm going to take the denominator and flip it. Well, so this would be, why do I have 3 here? Oh, yeah. So this would be 5 times k factorial all over 3 to the power k. Now notice I don't have any absolute values because they're unnecessary. Every number I have there is positive. So does anybody have a question right now? Okay, so the question is, what happens now? How do we handle this catastrophe? So before I do that, does anybody have a question?
Yeah, how'd you get 3 to the k plus 1 over 5 to
Okay,
the...
so there you go. Take the term. What's the that needs to be everywhere you see an n, you have to replace it with k plus 1. And then when I divide by a sub k, everywhere you see an n, I'm replacing with k. I don't need the -1 to the k because that's the absolute value of that is always 1.
Okay. And then why did you say you multiply by the reciprocal?
Because I'm dividing a fraction by a fraction. So if you come over here, a sub k plus 1, this is a fraction divided by another fraction. So how do you handle a fraction over another fraction? You multiply by the reciprocal.
Okay.
Now it looks way scarier here, but that's something you would have learned in like 5th or 6th grade when you work with fractions. But now it's just on a whole new level because it's not just numbers. Now, a lot of this stuff is going to cancel, so we have to be very careful how we do this. So the first thing I want to do, I don't want to mess with these. I don't want to mess with the factorials yet, but let's just cancel out what we can cancel. So if I look at this, let me take another color. Let's take maybe pink. This 3k will cancel with this power k up here, and all you're left with is a 3. So I'm going to pull that out front. And then I still have 5k quantity factorial divided by 5k plus 5. I'm going to distribute that 5 factorial. So make sure, but I don't want to go to the next page if someone has a question of how I got what I got. But I'm canceling those common factors of the 3's, and it leaves me with this. Oh, this is fun. Any questions about this? All right. So on the next page, I'm going to write out what this is. So I have my 3 times my limit. Okay, so upstairs I have 5k factorial. So let's write out, let's take our time. That's 5k times the guy who comes before 5k, which is 5k minus 1, times the guy who comes before that, which is 5k minus 2. And then this goes all the way down to, you know, let's even add, let's add the next couple. Let's add the next couple in. So who comes before that? Who comes before that is 5k minus 3. And then you go all the way down to 3 times 2 times 1. And then that's the numerator. And then the denominator, well, if you remember, it's 5k plus 5 factorial. So then you have 5k plus 5 times. Who comes before that? 5k plus 4. Who comes before that? 5k plus 3. And then that goes down to 5k. And then it's 5k minus 1. And then that goes all the way down to 3, 2, 1. Woo! So let that marinate, because lots of this is going to cancel. Actually, let me fix this because this looks very sloppy. I apologize. So this is 5k minus 1, and then this is dot, dot. So the beauty of writing all this out, and we'll take this little green thing, is lots of stuff's going to cancel. You know, the 1 and the 1 cancel, the 2 and the 2 cancel, the 3 and the 3. And then this cancels with a matching. This guy cancels, and this guy, they cancel with all the way up to here. So the only creatures that survive are the following. What survives? Well, the numerator, the only thing left is 1, but what survives downstairs? 5k plus 5, 5k plus 4, and then the very last guy would be 5k plus 1. And then upstairs is just the number 1. Now, this is a very, very simple limit because this is 1 over things that are going to infinity. So it doesn't matter how you want to contemplate this limit. This limit is nothing more than 0. And so the total limit is 0.
I have a question.
Yes.
Do you see like how you just went from 1 over infinity and then you got that equals 0? How
Yeah.
did you do that?
Well, just look at this limit and just ignore. Look here, just note. Here's what we're doing, and it doesn't matter. Let me get a different color. You just come over here and note. One over 5k plus 5, that's going to 0. Would you agree with me? I mean, as k gets large, where's that going? And if you don't, if you're confused or you're thinking like, what is he talking about? Just go to a calculator, or even in your head, imagine. Take 1 and divide it by a large number. What do you get? You get 0. So each one of those pieces in the denominator is going to infinity. So it doesn't matter. That thing's going to 0.
Okay, so it's like when I've heard like math teachers say when the denominator is going to a really large number, then the whole thing is just 0.
Well, okay, but you got to be careful. Not all the time. So if the numerator is a fixed number, which it is here, it's just the number 1. If the numerator is fixed and the denominator is going off to infinity, then you say the limit is 0. You don't. So you say the limit is 0. So that's how I'm getting this 0 over here. Now, if you want, I mean, look, you did these limits back in Calculus 1. I mean, really what we're using here is we're using this fact. You're using the fact that the limit as k goes to infinity of 1 over k is just 0. That's what we're using. I'm just using it I'm using it 5 times. So what's 0 times 0 times 0 times 0 times 0? It's 5 times 0 is 0. So you get 0. So what I'm inherently using here, without explicitly saying it, I guess, is I'm using the limit laws we had from back in Calculus 1. Now, back in Calc 1, we wouldn't have used the letter k, but it doesn't matter what letter we use. In Calc 1, you would have said 1 over x, the limit as x goes to infinity. And think about that stuff. Go to your calculator and take 1 divided by 100, then 1 divided by 1,000, 1 divided by 3,407. Keep making your denominator larger. Then when you divide it into 1, you're going to get numbers that are smaller and smaller. Does that make sense? Hopefully. I don't know. Now, another way to think about this, if you wanted, Kathy, is take that denominator. How many factors do you have? You have 5. Even though I put that dot, there's 5 of them in there. If you multiplied all those out, you're going to get a polynomial of degree 5. So you have 1 over a polynomial of degree 5. And then that limit is 0. You learned that actually before you got to calculus, back when you studied asymptotes, way back in like a pre-calculus course.
Okay.
So again, I'm not, when I keep saying you learned this before, don't take that as it should make sense right now. I'm just saying, I'm trying to remind you that these ideas have been taught at some point. It's just that we forget them. That's human nature. And one way to always feel better about what we're doing is go to a calculator and take 1 over a large number, and you'll say, oh yeah, it's 0. Because you could think about this limit right here that I'm putting the pen around. You could think about this as k goes to infinity. This is just 1 over a very, very large number. And what do we expect if we go to a calculator and take 1 over a very, very large number? We expect to get something very close to 0. That's the idea.
And if the numerator was switched, like
if the numerator is not a number, then you have a much more complicated scenario, which we talked about those back in Calc 1 as well. Sometimes it's easy, sometimes it's not. It turns out, though, when you're doing the ratio test, particularly in Calculus 2, where the examples are designed to work out, typically, 9 out of 10 times that you employ this ratio test, you're going to get something very similar to this, where it's 1 over something, and that limit's going to be 0.
Okay.
So here's the basic fact we're using from Calc 1. So we're using this. So this is from Calc 1. So we're using the limit as k goes to infinity of number over polynomial. We're using that this equals 0. And then the general case of this, which we didn't use here, you might also use this, which we used earlier today, actually. You might use this thing. So if you have polynomial over polynomial, if they have the same degree, it equals leading coefficient over leading coefficient. When the degrees are equal. So now I'm asking you to remember what all these terms mean. but you've actually used this a bunch this semester. We used it last semester. We actually used it earlier. I mean, when we did, if I go back some pages, if I used it right here. Notice that this limit on the page I have, this is, what's the degree of the numerator? It's 1. What's the degree of the denominator? It's 1. And so the limit is just the leading coefficients, 1/3. So you actually, this idea right here in the middle of this page, this is the one that you would have used in an algebra class or pre-calculus course when you were doing horizontal and asymptotes. You would have been taught this little trick. And then we gave you the real reason for it last semester, and now we're asking you to remember it. Does anybody have a question about this? This is good, though. It's good to go over these examples. They're not easy. At the end of the day, though, what do we know? So we know the following. After this work, we know this series converges by the ratio test. So if we summarize all this, heavens to Betsy. So in summary, since r, which is 0, that's our limit, is less than 1, the ratio test guarantees convergence. So now that we theoretically know it converges, if we wanted to know its sum, we can just go to the computer and calculate it. And we know that the computer's not lying to us. Fun times. Anybody have any questions about this?
Yeah, so if we use like the alternating series test, how do we prove that the series is like decreasing, going to
Much
0?
more difficult. You could, but the algebra is much more difficult because you have that factorial in there. Now you would just have to you'd have to just do some different types of algebra, but it's not wrong. You could use that if you'd like, but you would have to take use some more sophisticated algebra, and you would probably have to employ L'Hopital's rule somewhere or get creative, because that limit, you know, showing it's decreasing requires algebra, but you also have to show it decreases to 0. Which would require a sort of sophisticated limit. That's why I said, if I were you, anytime you see the factorial, Abdullah, go right to the ratio test and hope it works.
Oh, okay.
And I will tell you this, in Calc 2, unless I do it on accident, anytime you see the factorial, the ratio test will work. Now, I'm not saying that's true in real life, but I'm saying in Calculus 2, it's true. Does that make sense?
Yep.
Yeah. So, but yeah, if you want some fun, go try to use the alternating series test. See how far you get.
Is knowing which test to use like a matter of experience too?
That's 100% what it is. Just like with integration, knowing what to do is all experience. Experience, experience, experience. Now, you know, you could go and type this creature in the Wolfram, and it'll probably tell you how to do it. I'm sure the computer knows. It's sophisticated now. It could tell you which test to use. Let's see what happens if I do that. I'm gonna let me see what I can do for you. I'm gonna switch. This will be a fun little exercise that you guys can use. So if I go to share, let me go to, what screen do I want? I want this one. So let's say sum. Now, can you guys see Wolfram?
Yeah.
Yeah, cool. So what was the series? It was what? Sum. It was -1 to the n. What was it? Times. What did I do? 3 to the n? 3 to the n. And then this was divided by. Let me put some parentheses here. So this was divided by what? Was it 5n? 5n factorial?
Yes.
from 0 to infinity. I bet you it says converges by the ratio test. That would be my guess. Yeah, look at that. What a time to be alive. Oh, it even tells you what the sum is if you have any idea what the hypergeometric function is. This is what some of you buffoons would write on the test, because I would give you this, and then some of you knuckleheads would tell me that it's the hypergeometric function. You would have no idea what that means. But look, it even gives you the approximation. So I'm guessing if you pay for Wolfram, it will also tell you the steps of the ratio test. That make sense? Oh, here's a cool little exercise we can try. What happens? So does anybody have any questions about this? Notice how I typed that in. It's, you know, computer algebra systems can do series now, so that's good. If we go back to when we wrote out the first few guys, let's just look at this. So look at the first two terms. It's 1 minus 3 over 5 factorial. So if I just go to notice how accurate I am. Let me share this with you. If I just take the first two terms of my series, 1 minus 3 over 120, I'm accurate already. I am accurate to 3 decimal points compared to Wolfram. So pretty cool, if I do say so myself. So we know that Google Calculator is not lying to us because we know that it converges. So we're happy that it's working out this way. Okay, does anybody have a question about this example? Or does anybody else have any other questions on these problems at all? I'd be happy to talk about them. On the homework, going once. Trying to think. Yeah, some of these are easy, like T is easy. P series converges, you know. So someone wants to do D. I'm finding it. Yeah, so D, okay, D is a geometric series. We just have to recognize that. So it's you know, if you look at problems and look at A, B, C, and D are all geometric series. D is like kind of one in disguise because it has all these scary symbols. So let's get a different color. So what's this, our fourth example? So this one we have √2 over pi. K goes from 0 to infinity. So let you plug in 0, you get 1. You plug in 1, you get √2 over pi. You plug in 2, you get √2 over pi squared plus √2 over pi cubed forever and ever and ever. This guy is geometric. So it converges. Why does it converge? Well, what's its ratio? Well, you know that the square root of 2 over pi is less than 1. How do I know that? Because the square root of 2 is less than pi. And so what is the sum? So what's the sum? The sum we already know, since we're starting at 0 is 1 over 1 minus. So it's 1 over 1 minus the square root of 2 over pi. But some of us don't like to write it like that, so we multiply by pi, and we can write this as pi over pi minus √2. Woo! So that's a little more symbol crazy than the first three, because the first three you're going to get a number. Here you're getting a number, but it's written as pi in the square root of 2. So let that marinate in your brain for a moment. And we could even check that. Let's check that on, if I type that guy in on Wolfram. So if I plug this in, I guess I should share it with you. If I plug this in on Wolfram, you'll see that it gives me the same answer. Now they wrote theirs slightly differently, but I wrote mine as pi over pi minus root 2. Does anybody have a question about this? Going once. Going twice. I guess my head's. All right, so that's how you do D. Does anybody have a comment, question? How about any other examples? Does anybody want to do while we're at it? This was fun. Examples are good. Uh-oh, do you hear, we have screaming upstairs? My kids might be having a duel. I hear crying. Does anybody have a question? All right, I'm going to count to 5, and if I'm going to stop recording now, it's been fun. Oh, here comes something. All right, so that's okay, cool. We'll answer that after. All right, I'm going to stop recording. William, stay on, and then you can ask at that point. All right, so I'm going to stop recording now, and then I will upload all this stuff. Hopefully by the end of the day, everything will be caught up. So have a good one. I hope to see you guys Thursday. Be safe.